We shall begin with a little bit of story time. Yay, story time. This particular lab this week is Kirchoff's law. We will be discussing Kirchoff's law for the next hour and 15 minutes. It is a joyous lecture. It is because I have been working on this problem, learning on how to understand it and learning how to teach it for longer than you've been alive. I know, 6 years. I am, and it's, what is it, Yogi Berra who said it ain't lying, or it ain't bragging if it's true. I am the Kirchoff's law master. No one teaches it better than me. Who said it? I said it. When did I say it? Right now. So what? Are we starting to throw sass right now? So, I'm saying this because all last semester I took great pride in having you spin around in confusion by communicating with you that physics is a way of doing it many different ways, and it's okay to do a problem solve for this variable first and go to that one. But then we all knew how structured I am with vector addition. If you follow the rules of vector addition, you will not get the wrong answer. If you follow my rules, everything will be fine. This is another one of those moments. Kirchoff's law, do what I say, everything will be fine. Now, inevitably, about 10% of you to 20% will think of the following. Well, I talked with my mom's sister's ex-boyfriend's janitor who talked to his next-door neighbor down at the Quickie Mart, and he told her a specific way of doing Kirchoff's law, and I'm going to do it that way. You could do it that other way. I'm not saying there's only one way to do this. But if you do that other way, it's a lot like you going, he's just told me that if I don't jump in the Velociraptor pit, I'm not going to get my face eaten. So what I'm going to do is jump in the Velociraptor pit and then come to Dr. Eschenberg and say, how could you? The Velociraptors ate my face. Well, duh. If you don't do it my way, then everything will just fall apart. I'm prefacing this. I'm doing this with the idea that there will be students who go, I tried to do it a different way. And what happened? I've got no face. Exactly. So, this is the one time you do what I say. Now, let's do what I say. Kirchoff's laws, in the beginning, life was good. Life was one of those things where if you have a battery and you have a resistor, that the current flowing through that resistor is I naught, and I naught is the potential of the battery divided by the resistance. The easy way. And then we started moving into an environment where you had multiple resistors hooked up to the battery in strange and unusual ways. And it doesn't really matter how these things are hooked up. I'm really going for the point of so you know that if you have a series situation, that REQ is just the sum. And if you have a parallel, you have this. And we've become more familiar with these types of circuits. And in the last experiment that you did in lab, you did series, you did parallel, and then you did compound. And with compound, it was just a never-ending chain of squooshing to get it down into one particular equivalent resistance. Everything before had one battery. Now we work with this. Now, the numbering of the resistors do not matter. The strength of the batteries do not matter. At this point, the orientation or location of the batteries do not matter. What does matter is that we have to make some observations about what is going on. If we are here, now if I'm at that particular location in the wire, what is non-rhetorical? What is the potential? Did I put a ground into this? No. So if I don't put a ground into it, you don't have the reference point. So as written, this V is unknown. But if I said, all right, let's look at just the left side of the circuit. And one of the things that people ask about this is, well, what's going to be the bottom line in all of this? What am I going after? Well, the real question is, what is I5, and is the current bottom to top or top to down? Now, really what we're looking at here is that too bright to you or too dark? Or is it okay? Okay, it's okay. The whole, yes?
What is that side that come on the bottom left?
This? As written, this V is UNK, or unknown. My intention is we're going to spend the whole hour and 15 on this. Well, what we may end up doing is I'm going to explore this problem, and then once we get done, we're going to do another problem for real and speed it up a bit. Yes?
Even though you don't know the specific number for V1, could you say whether it's positive or negative just based on that?
When you mean by V1, you mean the battery here or the potential there?
Sorry, the potential at that point.
The potential at that point. The important part is not the specific potential at that point. The part that I'm getting at, and this is to answer the question, if you start here and you go from there to there, from there to there, from there to there, and from there to there. And we have all these other resistors that I don't, well, fine. R1, R5, and V1. If I start here and I go get to the potential there, to get to the potential there, to get to the potential there, to get to the potential there, I have a V start, and really, if I'm going to compute down delta V is where you start and you subtract it from where you finish. So what is the value of V finish minus V start if the path has taken you completely around the square? 0. Correct. And the analogy that I have, since there were people who answered quickly, which means there are people who don't understand what's going on, or even their own name. So the point is, if I start here, this has a particular potential. If this room is in Chicago, if this room is in Denver, if this room is at the bottom of the ocean, which means we have to move fast because we're all going to drown. If I start here, and I go up there, and I walk over there, and I come back down, and I walk over here, there is no change in height. If you start at the same position, if you finish at the same position, you're not going to get a change in potential. Much like when if I have a pen, like I did with MGH last spring, or last fall, if I move the pen across, there's no change in potential. If I move the pen like this, or like that, as long as those 2 points are at the same height, the change in potential is 0. That's the critical thing. So that loop has a change in potential of 0. So the change in potential, if you go from there is 0. If you go from there is 0 as well. The change in potential for both loops is 0. Now what we're going to do is we're going to have a loop 1, and we're going to have I should draw it more of a square. Loop 2. Kirchoff's laws make 2 loops and 2 equations are made from them. So we're going to create 2 equations walking 2 different paths. One path will be like this. The other path will be like this. Now, some may say, Dr. Eschenberg, do you always start in the left-hand square? Yes, I always start in the left lowermost point. Why? Because once you get into a routine, you don't like to mess with it. So you could start here, but if you start here, your loop must finish there. You must finish where you started. If you start here in this loop, you must go all the way around, because the delta V0, or equaling 0, is a critical equation that you're going to set up. And if it's not equal to 0, then a lot of bad things happen. You're not sure of the specific potentials, but you are sure that walking around that entire path, that the change in potential is 0. All right, next, how do we construct these equations? What goes into them that's so important? Well, we've kind of touched on it before. There are, in these types of problems, in all four cases, I'm going to go from left to right. So the blue line is the movement. When we're walking around these loops, we can either A, go from negative to positive lead. We could go from positive to negative lead. We could go against the current. Or we could go with the current. Now, if you are going from, or you're going across the battery, current is irrelevant. The current is irrelevant when it comes to the potential difference across a battery. When you're going from a positive to a negative lead, the delta V is equal to negative V, where V is the voltage of the battery. So if the battery is an 8-volt battery and you go from positive to negative lead, you're going to drop 8 volts, negative 8. If you go from negative to positive lead, you go from the negative to positive lead, the change in potential is positive V. And now I'm going to, oh, I think I can embarrass someone. Hey, Puff, are you in the room? Hands up. Excellent. If I go from a positive to negative lead across this battery and it's against the current, positive to negative lead against the current, what's the change in potential?
No, next part.
Is that your final answer? Negative? Because you're positive that it's negative. Let's not play games with this. So if the battery is 7 volts and you go from the positive to the negative lead, but against the current, your delta V is at 0, negative 7, or 7. Negative 7. Thank you, Bob.
I said it at the same time. Don't yell at her. She's gentle.
So Adrian, if I'm going with the current across the resistor, what is the change in V? I don't really have the equation up here yet, but since you're so keen on filling the room with your voice, Adrian. Mm-hmm. So what's Ohm's law? Give me and that's when I failed the class and set it on fire. I equals V over R. Solve for V. What is V now? IR. So if you're going with the current across the resistor, your delta V should either be positive IR or negative IR. If you go with the current, you're going downstream. So should your potential increase or decrease? Oh, it should decrease, which means the value should be negative IR. Now she's my friend, that's why I avoid asking questions. She's not. Question. Hold on, I'm talking to the person over there, the one who asked the question. I'll get to you soon. Yes.
So going against the current is like climbing a hill, going against
Yes, exactly. That's the analogy that I want to get. Going against the current is a lot like swimming upstream. Swimming upstream means you're going uphill, you're increasing potential. Is that your question?
Can you just explain what you mean?
Could I explain what?
With the current,
Okay. We're talking about resistors, not batteries.
Yeah.
So for resistors. Think of, this is how I think of this. a battery increases the potential. So the current, if the battery is right here where the positive lead is on the far side and the negative lead is on this side, it lifts the water uphill. The potential at the top of the hill is higher than it is below. A resistor in this case is a waterfall. So obviously if someone dumped like 10,000 gallons of water at the top of the room, it would all come down here. So the water's coming down. If I swam up against the current, the water is coming at me and I'm going against it. That means my potential goes up. If I start at the top of the hill and slide down with the water or with the current, that means the potential drops. So let me write this down. So I'm including the signs in all of this. If you go with the current, your potential decreases. When you go against the current, your potential increases. Against the current, upstream. With the current, downstream. Downstream, downhill. Up the current, uphill. Increase in potential. So these 4 rules you're going to use when you construct your equations. Just patting your head. Okay. So we know we're going to have to put together 2 equations. They're now rubbing their heads and patting their stomachs to see if they can do that switch thing. It's very, really serious. Now, let's talk about this equation, or this circuit right there. When you first do these problems, you're gonna have to get an idea for what the currents should be doing. By just looking at this, there's about a 90% chance that you're going to get it right. When looking at this, current from a battery, unless it's completely overwhelmed by another battery, this current from this battery should go like this. And this current from this battery should go like that. So in the end, this I1 that we're looking for should be clockwise. And this I2 that we should be looking for is counterclockwise. Ideally, the current on the left, the way that the batteries are set up, should be clockwise. The way that the batteries are set up, the loop on the right should produce a counterclockwise. Now, that's an idea for what we're doing, and I'm going to now pick some resistors. 3 ohms, 6 ohms, 2 ohms for the 2, 12 for the 12 for the R4. I need 18 for the R5. Now what I'm really doing is I'm looking, Kirchoff's law, I'm more interested in the technique, I'm less interested in the numbers. So the way that I set up Kirchoff's law for tests is all the resistors on the left, all the batteries on the left are going to have a certain common multiple. The ones over here, I've decided to make it 3. All the ones on the right need to be a multiple of 2. And that's to make things more simple. So these are the numbers. Now, the number that I'm really looking for is the current running through the middle resistor. What is the current running through the middle resistor? Is the current going from bottom, top down? Now, what I've told you guys to do, and this is something, the first time I ever really taught this versus the way that I'm teaching it today, there has been an evolution in how I teach it, mostly because no teaching lesson is student proof, because students can be just so resourceful in their confusion. So this is kind of the current flavor of how I teach this now. When we have a number line, and let's say the coordinate of the number line, we're going to call it J. Why not? What I'm going to do is I'm going to call this the current. If J is negative, what?
Just trying to get your,
What do you want?
will you please turn the page back for like a minute? Thank you very much, I appreciate it.
You're welcome.
Is R5 18?
R5 is 18, R1 is 3, R2 is 2, V2 is 8, R4 is 12, R3 is 6, V1 is 12. Volts and ohms, respectively. May I now turn the page?
Yes, thank you.
You're welcome. So if you have a current, sort of like a velocity, negative velocities left, positive velocities right. So that's negative and that's positive. And then what did we do with the coordinate system for Atwood's machine? We took it and we bent it. Excellent. So now, negative values are up and left. Positive values are right and down. Now we have reached the conclusion of our number line bending by if the J is positive, the current is running clockwise.
So why are we using J not on the current?
Well, that will become apparent later. And there's a rant behind that. There's a story. If J is negative, it is a counterclockwise current. Now, what I'm going to do, well, let me explain. Let's do the setup of the equations, I think. That would be best. So getting back to this, we construct two loops equations, loop 1 and loop 2. In both cases, the delta V is going to equal 0. So the delta V for loop 1 is 0. The delta V for loop 2 is 0. And what we do with forming our equations is we walk the path. We start here. We first encounter a battery. that battery encounter goes from negative to positive. And we get positive V1. Now, what we're going to do is we are going, not going to treat J as a clockwise current. We're going to make that initial assumption that when you're walking in a clockwise fashion along the path, you are walking with J. You are walking with the current J, which means in the second part, we are going from there to there across R1, and this is minus R1J1. We walked with J1 because J1 effectively runs like this, and J1 goes with R1, so it has to be a minus sign.
Why does it have to be?
Because you're traveling with J1. In all of these cases, with the exception of the middle resistor, you're traveling with the current in the loop. Always. The one exception being the middle, and I'm going to do that right now. In the middle resistor, here, you have the top of the resistor, you have the bottom of the resistor. The top of the resistor sees that J1 is going from top to bottom. But when you're going from top to bottom, J1 is flowing from top to bottom, but J2 is flowing from bottom to top. So when you travel from there to there for loop 1, it is minus R5J1 plus R5J2. Yes?
Why is J2 flowing the other way?
Because when you have these currents set up, J1 is clockwise. J2 is also clockwise. But through the middle resistor, that resistor is on the right-hand side for J1, meaning the current comes down. The resistor is on the left for J2. That means that the current goes up. And that is why this particular part of the equation, there to there, you're going with J1 or minus R5J1. You're going against J2, positive R5J2. That is the only point in the loop 1 equation where current 2 is being used, J2. And then the last part in the loop,
How do you tell just looking at that image that it's going with or against like that?
what I did is I drew in both cases, oop, I shouldn't have done that one. Yeah. So what I did is I separated the two boxes, and let me blow it up so that we can look at this. Whoa. All right. The loop on the left is loop 1, and we're currently producing that equation at the moment. We started in the lower left, we go to the upper left, we go to the top right, and then we come down. Start for loop 1 is at the top of the resistor, end for the moment is at the bottom of the resistor.
So that's gonna be given? Or?
It just is. Is the floor given? Just is.
So it's always gonna start at the top and
It's always, well, for loop 1, it's always going to start at the top. When you do both of these loops, you always walk in a clockwise fashion. For me, I always walk from the lower left clockwise. So I walk from bottom to top, and then I walk across the resistor at the top, and towards the end of the problem, I'm going to walk across another resistor. In those three cases, there's only one current, J1. J1 is run clockwise. This speed, or this current velocity. When you go from start to end for loop 1, you're in the middle resistor. The middle resistor, when you go from top to bottom, now I'm looking at you. When you're going from top to bottom for loop 1, are you going with J1 or against J1? Top to bottom. The current for J1, when you're looking at the start of the loop, is flowing in this direction. So the current J1 at the start, the current is coming in at the start and coming down at the end. So you're going with the current. Now look at J2 for loop 1. When you're starting at the top and going at the bottom, are you going with or against J2? Still looking. With, against, I don't know. Let's try again. J2 is running in a what fashion? Clockwise or counterclockwise? Don't look at the paper, look at me. It's running clockwise. And so since J2 is on the right, the current is coming up from the bottom and out the top. So if you're going from the top to the bottom, as J2 is coming in the bottom and out the top, are you going with J2 or against J2? Against. And so that is why, for these middle resistors, loop 1 it's like this. When you're going from there to there, you are traveling with J1 current but against J2. That's why that's negative and that's positive. When you're going from there to there, you're going against J1, which means that the change in potential is positive, and against or with J2, which means the potential difference is negative. So that's how those parts are set up. In the last bit of the loop, you're going from there to there across R3. Oh, thank you. Minus R3J1. And that is the construction of the first loop. I went from negative to positive across V1. I went with J1 across R1, negative R1, J1. I went with J1 but against J2 across R5, producing those. And I went with J1 across R3, producing that. Question.
So for every battery in a loop, you just have to, like, you only include the resistor that just in that one loop.
Mm-hmm.
Can you put the bigger picture on here?
Oh, the bigger picture up with the second loop. This one. Now let me draw loop 2 real quick. I start in the lower left. I go against J1 but with J2. Positive J1 R5 minus J2 R5. The next part, with R2, or with the current J2 across R2. So minus J2 R2. Then I go from positive to negative lead across V2, minus V2. And then with J2 across R4, minus J2 R4. And now we get our green and red pins. In a problem like this, and this is going to be on the test, test 2, Kirchoff's law, metaphysical certainty that it will be on the test. You will be given a situation like this, and then you'll simply be asked, what's the current flowing through the middle resistor, and is it from the bottom top or top down? That's it. That's the question. On Blackboard, our copy machine is currently being a nuisance. On Blackboard, the current problem set is available. It is due a week from today at 6 o'clock. All of the voltages and all the resistances are known. V1, R1, R5, R5, and R3. R4, V2, R2, R5, R5 are known. The unknowns, J1 and J2. We have two equations with two unknowns. Dun, dun, dun. And a little part of your soul dies inside. It's all it is. The core of a Kirchoff's law problem. Some professors tend to make it more complex. Let me tell you right now, I know you guys are a little bit unappreciative of what I'm doing. Now, facetiousness is breaking down. Hold on. I'm now going to pause my rant for Adrian. Question.
Why for loop 2 is it not like delta V2 equals 0 equals negative V2?
Negative V2 is there. It's the next to last term.
Yeah. Okay.
Now, when I walk the curve on the right, I also walk it in a clockwise, which means I go through the middle resistor first, then R2, then V2.
So V2, negative V2 is just not like
It's because I went from the top down across the V2, and that's it. Some professors teach this. You're going to give me the right answer, the right response to this. Some people teach this like a 3 equation, 3 unknown problem. Which do you prefer? 2 equations, 2 unknowns, or 3 equations, 3 unknowns? 2 equations, 2 unknowns. Are you thankful for that?
Of course.
Yes! You're thankful to be alive. All right, the way that this thing could go down is that it could be set up as a 3 equation, 3 unknown, which would make it a nightmare for everybody. You guys are future doctors and pharmacists, and you can barely hold on to a 2 equation, 2 unknown. Let me throw in a 3rd equation and a 3rd unknown, and just watch kids start falling from the balconies. So it is this simple. I'm trying to make it as simple as possible. I'm trying to help. Now, granted, I do understand it is 8:53 in the morning, which means appreciation is not freely given at this time of day. So I understand. Question.
Okay, I know we've talked about this and all, and I have written that you said the current in the left box should be clockwise and the current in the right box should be counterclockwise.
Yeah.
On loop 2, why do we walk it counterclockwise?
I always walk my loops clockwise. I always have my J's run clockwise. I always assume that the currents are running clockwise at this moment. The question that you've asked is similar to the question that someone else asked, and it's going to be addressed. I'm not done yet. I really enjoy spending an hour and 15 minutes on one problem. It's awesome.
J was positive in the very first thing you
I
did.
treat my J's as positive.
That's why.
I just assume J's are positive.
That's why.
J's are positive and J's are running clockwise. Now we're in math mode. Simplify this. 0 equals V1 minus R1 plus R5 plus R3 J1 plus R5 J2. All I did in this particular case was I factored J1 out of this, and that. Or negative J1, pulling the negative sign out and putting the J1s there. Here, 0 equals minus V2 minus R5, R2, and R4 positive R5J1. Now normally I'm not in a very giving mood when it comes to plugging and chugging in the middle of the problem. But the one thing that I have learned is plugging and chugging it now will make things a lot easier.
You're missing something.
I am missing J2 there. So let's plug and chug. 0 equals V1. I'm going to need this thing. V1 is 12. R1 is 3. R5 is 18 or 21. R3 is 6. Whoops, that's 27. That's not going to factor out well. R5 is 18. J2. So this numerically has been simplified. Second equation, minus V2 minus 8 minus R5, 2, and 4. So 2 plus 18 is 20 plus 12 is 32. 30 minus 32 J2 plus 18 J1. Now one of the things, it is slightly, common factor of the first equation is 3. Common factor of the second equation is 2. So what I'm going to do is I'm going to take this equation 1 and divide by 3. So 0 equals 4 minus 9J1 plus 6J2. An equation, and I'm going to start solving for stuff right now. 9J1 equals 4 plus 6J2, or J1 is equal to 4 plus 6J2 divided by 9. I'm setting it up so that when I take the second equation, I can just slap a J1 in there of this and then move on. Let's take this J1 and put it in there right now. 0 equals minus 8 minus 32 J2. plus 18, 4 plus 6J2 divided by 9. The 18 and the 9 cancel. Distribute the 2. 0 equals minus 8 minus 32J2 plus 2 times 4 is 8. 2 times 6J2 is 12J2. Oh, crud. This thing, the numbers ended up horrible. Because the way that the numbers have been set up, okay, fine. Let's just do this. Minus 8 and plus 8 cancel, which means 0 equals minus 20 J2, and J2 is equal to 0 amps. So the way that the raw numbers have been set up, and I will go over, it's a number. Whoopee. There you go. The current running through J2 is actually nothing. It can happen. It depends on how the battery and the electronics are set up. Now, ideally, what should have happened, we'll go over the permutations later. If J2 is 0, that means J1 is 4 plus 6 times 0 divided by 9, or 4/9 amp. And it's a positive 4/9 amp. The reason why I've got 0 is because of some quirk of number choice. It just worked that way. 0.44 amps. So the current on the left, that J is equal to 0.44 amps, and the current here is 0, which means no current runs through those 3 sides, and you got the simple one. 0.44 amps go from top to bottom. And so the middle resistor has a 0.44 amp current running through the middle. Now let's talk about how reality is going to happen, particularly on the tests, because when the tests come, I have a spreadsheet of a Kirchoff's law problem. I derived every value needed, and I just sit there and I plug in numbers. This was just random. Usually, one time, oh my God, there was one time during a final where the answer for J1 was equal to -1 and J2 equaled +1, so that the current going through the middle resistor actually was 0. Like I had it tuned up where the current in the middle was 0. And people flipped out. They lost their minds. It's a number. Deal with it. So fine. Under normal circumstances,
0 makes people think they did something wrong.
yeah. If I would, okay, let's do this. I've got a copy of Gene Coley. I promise you on the test that J1 and J2 will never be 0. This was just, even on the final. Now, truth be told, if you guys do well on the Kirchoff's law for test 2, it won't show up on the final. So if you kill that problem in test 2, there's no need for me to test it again. Because I'll be putting an Atwood's machine problem in the final. Try to figure that out.
Really?
I
Please tell me you're good.
don't know. I have to work on that one.
Please tell me you're good.
Usually. Now, I want to do some examples that addresses her question of, well, if we could tell at the very start that this thing was going to run counterclockwise, how come we didn't set it up to be counterclockwise? Well, answer A, Answer could be 0, which means that the current doesn't run in any particular direction. J could have several values. Let's say +1 and J2 is -2. And J1 is equal to -1 and J2 is +2. All of these are in amps. 12 minutes, we're going to use them. Now, these are hypotheticals. Let's say we do our 2 equation, 2 unknown, and in the first case, we got a J that's +1 and J2 is -2. What do we do then? We now know positive is a clockwise current. So now I'm going to draw I1 as a clockwise current, and I1 is 1 amp. I know that J2 tells me that this current is running counterclockwise. So I2 is counterclockwise, and I2 has a magnitude of 2. The way that I associate J is that I think of it as current velocity. Current velocity is negative, so the current is counterclockwise. I think of current I as current speed, the magnitude. Now, the thing that I found, and this is the main reason why I use J, is because I'll get to your question in a second. I normally use I. And if I get a negative I, I'm perfectly happy with negative I. That just means the current's running in the opposite direction, and I can figure it out. What I found is, if I use I and I becomes negative, what the student does is they take that number and then they go back to the second equation or whatever equation should have a negative current and flip all the signs and rework the entire problem. It is a colossal waste of time. The only way that I've toned down on that happening to prevent that is I use J and say J is current velocity. It can be negative, it can be positive, and current speed, which is I, which I treat as always positive. And then the students tend to go, okay, I accept that. And I'm not happy with the way that it works. Most physics majors would look at that and go, well, that's just a waste of time. And then they do it the way that I would normally recommend it. But it's the best. I've found at the pre-med level that this technique works out the best. Question.
So if J is a negative value, it's running counterclockwise?
J means that the I is running counterclockwise.
Okay.
If J is positive, the I is running clockwise. If J is negative, the I is running counterclockwise.
So on that I1, is it counterclockwise?
J1 is positive, so I1 is clockwise. J2 is negative, so I2 is counterclockwise.
Oh, I was looking at the bottom.
Yeah, you didn't draw.
Oh, for this one? Well, let's do this one. Now notice how I drew them. I drew the arrows where they are with respect to the center resistor. In a case where J's are opposing signs, this is a good thing. Because in either case, the currents are either flowing together top to bottom, or they're flowing together bottom to top. If they're flowing together, all you got to do is add. So the current for 5 is 1 plus 2 equals 3 top to bottom. For this one, I5 is 1 plus 2 equals 3 bottom to top.
So that bottom to top just deals where,
It just tells you where the direction is going for the current.
does it change based on how you add your battery?
Yeah, it's all based on, however these numbers turn out, these things are dependent upon those. 7 minutes. The other two possibilities are J1 equals positive 1, J2 equals positive 2, J1 equals negative 1, J2 equals, negative 2.
Can you explain the arrow?
You mean these or
Like down or?
this?
Yeah.
Look at how these arrows are going in the middle. This one is running clockwise, that is running counterclockwise, but in both cases they go from top to bottom. So that's why you add the I's. This one goes counterclockwise, that one goes clockwise, both cases bottom to top. So if they're both going in the same direction, to figure out the total current, you just add the magnitudes. In cases like these, these two are both running counterclockwise. These two are both running clockwise. But in each case, they're opposing each other. In the middle, the left one is top to bottom, right one bottom to top. For this one, bottom to top, top to bottom. So in this particular case, the I in the middle is equal to the I that's bigger minus the I that's smaller. Because I1 is now 1, I2 is now 2, so I in the middle is 2 minus 1, which is 1 amp. The bigger one is the one on the right, and it's going from bottom to top, so it's 1 amp bottom to top. Over here, once again, I in the middle, I1 is 1, I2 is 2, I in the middle is 2 minus 1, which is 1 amp. The bigger one is the right one, the bigger one is from top down, so the current is going from top to bottom. And that's the basis of Kirchoff's law. What I'm going to do, I've got like 15 of these introductory Kirchoff's law lectures. I will post one of them where the answer isn't 0. And then you can see how a non-zero solution looks like. But this is the pattern. The fact that the number is 0 means nothing. The logic of what I showed you, the procedure that I showed you, that controls everything. Problem set is available. Thursday is magnetism. Thank you. And happy Mardi Gras.